person and on Zoom for colloquium today. I have the enormous pleasure of inviting Viviana Aquaviva to be presenting to us today. Viviana is an astrophysicist who is using data science to study the universe, which is really exciting for basically everyone, regardless of their specific discipline of study. Currently, she's a professor in the physics department of the New York City College of Technology and the CUNY Graduate Center. She's a long-term visiting scholar at the Flatiron Institute Center for Computational Astrophysics, and she is a Harlow Shapley visiting lecturer for the American Astronomical Society. She's an innovator and advocate for the application of machine learning in physics and astronomy, and she's been highlighted as a techno-visionary and one of Italy's 50 most influential women in tech. She was also listed as one of the 50 women who are doing the history of computer science. So, with that in mind, no pressure, Viviana.
No, absolutely. No, I'm very glad that I didn't let you read this to me before.
But we are delighted to have her with us this week. And I will also mention that in addition to being here to discuss her research, Viviana has been kind enough to lead a workshop for us tomorrow on building community and finding mentorship in our careers, which regardless of your phase of your career is very important, and all are welcome to join us then. Thank you so much. I will give this over to Viviana. Thank you.
Wow, well, thank you so much, Sophia, for this wonderful introduction. It is truly a pleasure for me to be here, and thank you, John, for having me, and Flor, and all the people that are making this visit really special. So what we're going to be talking about today is just some sort of like adventures in the study of galaxies. And so, just the basic idea there of how we study galaxies is that what we have, what we can learn is some sort of emission charts of the brightness of galaxies at different wavelengths, right? But what we really like to know are physical properties of galaxies. Things like, how many stars there are, what's the star formation history, what's the dust content and distribution, the chemical enrichment and its history, redshift, and so on. And so for many, many years, the name of the game, the only way we were able to do this was spectral energy distribution fitting. And I have to say, this is truly like the first data I worked with. It was like about 12 years ago. These were like stacked Lyman alpha emitting galaxies at redshift 3.1. So I made that slide then, and I just can't let go. So I just keep showing it and showing it, and at this point it's like an antique. So one of the problems that we have is that we would like to know these physical properties, right? What we have are some measurements, sometimes pretty, not particularly exciting like this one. But we actually need another ingredient. And the ingredient that we need is models. And so once we have models, we can, start playing this game where, like we try a model like this red one that, as you can see, doesn't really go through the data very well. And then we can try another model and then another model. And when we find something like this that black model, which actually was the best fit at the time for this data, we can say, okay, I know what are the physical properties of the model, and the model seems to resemble the data, so I conclude that those are also the properties of the data. And I can infer the property of the galaxy that I observe. So now I have to say that I love acidity fitting. It is, I think, the way we will continue to learn about galaxies for a long time. It's also what got me a faculty job, so I have a particular debt of gratitude. But I think in the years, and especially in the last decade or so, we've also learned about its limitation. So one of the biggest things is that every time we create a model for something that is as complex as a galaxy, and we said, okay, galaxy, I'm going to describe you with like 5 parameters, 6 parameters. We're making these huge simplifications, right? And if it's just us deciding what parameters are important, this is, an almost guaranteed way of introducing bias. We also have other issues like, we do things like using Bayesian statistics, but we don't know what priors we should use. We know that our sampling methods have limitation. It is a very time-consuming business. And so a few years ago, actually about 5 years ago at the time, I decided, I was fascinated by what at that time was the road less traveled. And so I started using machine learning methods to see if we could learn something about galaxies with them. And the first exercise that we did was to see if we can learn about the star formation histories of galaxies using machine learning. So this was a work led by Christopher Lovell, who at that time was a graduate student and is now a postdoc at University of Hertfordshire and actually moving to Portsmouth as a CM fellow. So the idea there, what we said is like, okay, clearly, the problem with this machine learning method is that we can't learn from data directly. But if we believe that simulations are informative enough, then we could do something like this. We can take what at the time, again, were, well, still are, state-of-the-art cosmological simulations, in this case, Illustris and Eagle. We use flexible stellar population synthesis models that I'm sure people here are very familiar with to generate realistic spectra. And then we use a convolutional neural network to learn the relationship between the things that we observe, that are the spectra, and the things that we want to learn, which are these star formation histories of galaxies. And one of the reasons why we use two simulations that we said, this way we can see what happens when we learn from one simulation and apply within the same context, but also what happens if you do things across simulations. And some of the good thing about these aspects, I really don't want to push the idea that this is superior to SED fittings or that this has no biases. But it's just like an alternative method. And so one thing that is an advantage is that sometimes when we do traditional inference, we have to specify models, and here we can be a little bit more general. And another thing is that when we learn from what in machine learning is called the learning set, we learn not just about the single objects, but from the population. Something which is a bit like, but I really don't know enough statistics to tell you whether or not this is rigorous, probably not. But it's something which is a little bit close to learning at the same time the likelihood and the priors in traditional inference. On the other hand, anything that we learn from machine learning tends to be a little less transparent in terms of interpreting the results that we have. And then the biggest thing really is that there is no ground truth to learn for. So, we are relying on our simulations being realistic, right? Or actually, our simulations having some degree of truth to them. And understanding whether or not this is reasonable is something that I spent a lot of time thinking about. And you can think, okay, are there other ways in which I can train on data? Are there some galaxies for which perhaps I can find their star formation history some other way? And I think maybe in the local universe this is possible, but it's not something that is in general easy to do. So anyway, we decided to do this exercise, and this is a result of just the kind of setup that we have. These are like 6 examples of galaxies, and the red and blue curve is their star formation histories. We divided them in bins in which they are constant. These bins are, going in look-back time, and they are equally spaced in log because, of course, we know that we are a bit more sensitive to the recent history compared to the very past one. And here, the truth, and when I say truth, I mean from the simulations, is in blue. The ones that we predict are in red. And you can see several examples that are sort of fits in the, fit 20th, 40th, 60th, 80th, and 95th percentile of our metric. Means that, on the top left corner, you see one of the best examples. This is also one of the easy things, an almost quiescent galaxy that formed all its stars a very long time ago. And then here, you see something that we can't do very well. Galaxies for which basically we are missing, actually we are over-predicting the star formation history at relatively recent times. So this is sort of like the span of how well we could be. But in general, now I didn't post a median anywhere, but I guess that here, the metric that we are using, something called SMAPE. I tried for a long time to find an acronym with SNAPE, but I couldn't, so I settled with SMAPE. So the SMAPE is this like symmetric median absolute percentage error. It's a way of doing something that is percentagey, but also not dividing by the star formation rate in each bin, because for quiescent galaxies, you will be dividing by 0. So instead, you normalize by the total star formation rate of a galaxy over time. And so here, but it is, somewhat in sort of like a low error regime, it is somewhat similar to a percentage error. And so you see that we are around 15% in each bin, which is actually not bad at all. But this is, of course, within the same simulation, right? So that's the easy thing. You learn about illustrious galaxies, and you applied it to the same. Then we also did the exercise of learning on one simulations and apply to the other ones. And so now, basically, we move from these, were they dashed? I don't even know. These like point thingy curves to the solid ones. And without going too much in detail, you can see that we can say that basically this MAPE, the error, doesn't blow up. And so we call this a good thing. We did a victory dance. I feel like the conclusion of this process that took actually a couple of years is the fact that we still were faced with the same issue. We trained these models on the simulations. We applied them to real data. And on real data, we don't have some truth that we can check, right? And so we're always, and we should be, skeptical of what we have learned. So my question for a long time was, what would it take to trust the machine learning models on data? And I think we can agree that if the simulations and the data were absolutely identical, right, from every point of view, every observable that you can come up with, they're the same. Then I think we could be satisfied. You'll be like, okay, you learn on this one, you can apply to the others. They're essentially the same. But I think we're all willing to conceive that even if simulations or data are not identical, but they're similar, there is still some degree of believability that our models are bound to retain. And so my idea was that, is there a way that this can be quantified? Can I use the similarity between simulations and data to also quantify how much I should believe these models that are trained on simulations? So here is my idea. This is going to be a bit of a crowded slide. Let's say that there are these two spaces, right? One is the domain where I train my models, in this case, simulations. One is the domain where I apply the models, in this case, data. Right? And these weird shapes that look like, I don't know, vaguely about heart was my attempt at domain adaptation art, but this is still spectra, okay? So there's nothing mysterious about that. The observed space is still the space of spectra. Now, in this space, I can define, I haven't yet, and I won't for a while, but I can define some measure of similarity. This is the space in which I can tell, okay, these things are similar or different. Now, there is also, a more interesting space, which is the space of inferred properties, right? And so in this case are things like the stellar mass or star formation history or dust content or whatnot of a galaxy. And nature goes from one to the other with some function, right? Here I'm calling it F. This is the true way of saying, okay, if a galaxy has these properties, this is the spectrum that you will observe. Of course, we don't know this one. In the simulations, on the other hand, I still have physical properties in the simulations, and there is a function, which is my modeling function, that brings me from here to here. Now, in reality, I'm not even, this is very interesting, clearly, right? This is what nature does. But this is not even what I really want to know. What I would love to know is the inverse of that function, right? What I really would like to be able to do is to observe some spectra and being able to infer the real properties of galaxies. And of course, I can't do that. So the best proxy that I have is the inverse of this function. This is a function I can learn. Not perfectly, but at least on simulations, I can say, okay, because I know how I do this step, I can also do the inverse process, and I can figure out how to infer physical properties from spectra. Okay, so here's my hypothesis of connecting this framework to the idea of distance. Let's say that we are just in simulation space, right? So in simulation space, I have these physical properties. I have my modeling function that brings me to the simulated spectra. I can learn my inverse function, g to the minus 1, that gives me the inferred physical properties. So of course, they're not going to be the same, right? Because in real life, I'm limited by many things. I have a limited size training set. I have degeneracies. I have observational errors, all sorts of things. So I end up with some distance here, which is an error. And I mean, if we want, we can decompose it. But if we're not machine learners, this is not particularly interesting. Now, I can now move on to observe spectra. And as I said, here I can define some sort of distance metric that measures how different the observed spectra and the simulated spectra are. Now, if I try to infer the physical properties from observations, I know that I have these unknown functions that brings me from the true ones to the spectra. Can't do anything about that. The only thing I can do is to apply the same functions that I learned on the simulations to infer the physical properties of the real spectra. And so far I have said anything new. Now my hypothesis is that there exists a distance metric d, which I have to find, right? So this is, this is a hypothesis, it's easy. But there exists such a metric so that the error that I make here when I apply this inverse function to data is just an additional bit of the total error budget, and which acts like a bias, which is sort of like a difference in the average distance between the predicted and the true values. And the big hypothesis here is that this bias is proportional to that distance. Right? So I'm saying the additional error that I make is proportional to an appropriate distance metric that I have to find. And I had the idea that this had to be true. But I still don't know. This is like, 3.5 years later. So this is just to describe, the pace of my research. But, I thought, okay, I think that this, I have an intuition that this should work. So at that point in 2019, 2020, very uneventful year, but I was on sabbatical. And so I spent a lot of time studying papers, especially in computer science, that describe how to measure distances between distributions, right? There's a lot of literature around it. You can imagine doing a low-dimensional projection on your data and measuring distance in that space. There are things like, looking at summary statistics. You can do things like this Earth mover distance or the KL divergence. A lot of things that I've studied and tried didn't bring me anywhere, really. So at the end of this beautiful year, I just decided I had to scratch this whole thing. And I will tell you what I think I've learned, what I think is true now. And I realized that, this is also not very likely to be true, but this is how we proceed. So what I convinced myself of in the end is that all of these methods assume that we can measure distances between data sets without regard for the problem we're trying to solve. Right? I might want to, do I want to determine stellar mass? Do I want to find the star formation history? Do I want to find metallicity? Do I want to find redshift? In general, when I just measure distance between data sets, in my case simulations and observations, I don't know about this problem. And I convinced myself that this is not a promising approach because, for example, let's say that I'm trying to measure stellar mass. We know the information about stellar mass is encoded in the rest frame near infrared, right? And if I were to look for things about dust, I should be looking in the ultraviolet or in the far infrared. And so whether or not my simulations are realistic in a specific regime will matter on whether or not I can trust the models that I built on simulation for a specific problem. So I figured that this may be a reason why all these other approaches I had been considering didn't work. And so what we did instead was to say, okay, let's just do a very simple measure of distance, Euclidean distance, but in a reduced space. And this reduced space will be the space of the most important feature in a spectrum to solve a given problem. So in a way, first I build the model that says, okay, I want to predict stellar mass. I have a good model. Then I look, okay, in the spectrum, what are the bits that give me information? And then I look just at that space, and I calculate a distance in that space. So this was my new great idea. 3 years of work, this is what I'm with. All right. And we thought, okay, where do we test your ideas? Clearly on the simplest examples, which is stellar mass. So, and of course, we still had to test on simulation, right? There's no way out of this. So what we did is the following. we started with like 20 sets of simulations. And the idea was that, we know that, as Flora reminding us actually earlier, a lot of variance in models come from all the systematic effects that we know. We don't know how to model. So we have a lot of space, of room for variance there. So we picked 20 of them to sort of represent this range of uncertain things. And then we calculate the distance between each data set, right? It's a matrix of like 400 distances. Fine. Then we train 20 models, one per simulations. We train 20 models to learn stellar mass. And this means that we basically learn 20 inverse function g to the minus 1, one per data set. And then, this is the bit that I always get confused in explaining. Let's say that we fix one function, right? The inverse function g that I learned on my first data set. Now I apply this inverse function to the other 19 data set to infer the properties on those. And now I have 19 errors, okay? And then I put in a plot like this, the distance metric between the data set that I'm using a reference, in this case it was the first one, and the error that I do on all the other 19 data sets when I apply that function on the other ones. So I have 20 plots like this, right? I can only show one. I mean, I could show the 20. It's not particularly interesting. But basically, I end up with 20 plots like this, and I ask myself, do I have a reasonably tight regression relationship? Because remember, my hypothesis there, is there a distance metric so that these two things are proportional to each other? It doesn't even need to be linearly proportional. It just needs to be predictable. But in practice, we always want lines. No, lines are much better, easy. So I'll show you one. And this is actually simulation one. I haven't picked this, I can promise. And this is what we had. And the main reason why I'm showing this is that because I was very proud of this paper title. So it is a reasonably tight relationship. I mean, somewhat. It's a decent correlation. It's not perfect. You can see that there is, like those clusters of 4 points up there that actually have a different modeling of binary stars that are a bit different. But the reason why I think this is exciting, and perhaps I should have mentioned it earlier, but since I didn't, let me do it now, is that if I have some sort of regression relationship that I can trust, now here on the x-axis, I can put the distance between the simulations and the data. And then I can just read off the error that I should be making from my regression. So this is the game that I wanted to play. If I can find the distance, so that distance and error are proportional, distance is something that I can measure even on data. And so I have an idea of what would be the error that I would be making when I apply my algorithm to data. So we got to this point, where are we at? Yeah, December 2020. And then we said, okay, maybe, we knew that the distance that we were using, this Euclidean distance, is like, very basic. And so we knew we could do better. We wanted to also, see what happens when you're not just predicting stellar mass, but other physical properties. But how life always takes a different path. And so instead, what we ended up doing was working for a couple of years on this different problem, which is, are spectra the best way to encode information about galaxies? And as you know, whenever you ask a question in a title, the answer is always no. But this is something that we probably know. We know that if we just use brightnesses and neighboring wavelength, this is a very redundant set of features. And redundant in general in measurement is bad, because then it means like super correlated with all sorts of complications. Another thing that we had in mind was that, for example, when we do regular spectral energy distribution fitting, just Bayesian statistics, we know the colors are more informative than magnitudes, right? And so we had this idea that perhaps we could use different features that were more related to the shape of the spectrum rather than just, sort of like point-like measurements. So we explored two ideas. One was to look at all the features that we have and cluster them according to how correlated they are. So we create little clusters of features that are very correlated. And this has, like two advantages. One is that you can reduce correlation. The other is that you can reduce dimensionality. The other was to create what we call the superset of features that has also shape information. So I'll start from the first. Right? Our goal was to say, okay, can I find from just the brightnesses some sort of subset of features that are less correlated with each other, still physical, and that doesn't yield any information loss. And the idea of physical was important for us because anybody who has like any knowledge about data analysis method will tell you, hey, there are these so-called encoders. There's tons of them. Right? And an encoder in machine learning is simply an algorithm that learns to replicate an input, but just goes through a bottleneck of lower dimensionality. So it's very, very easy to find the latent space of feature, which are some complex nonlinear combination of your features that encode all the information that you want in a much lower dimensional space. The problem with this is that you cannot interpret it anymore. And for us, we thought that interpretability was important. Right? Being able to say, okay, I'm solving this problem, and look, the indicator that I'm looking at is this. And you can actually map it to a physical feature that then you can go and measure is important. Once you lose this, you also lose information about what is a good set of things to observe. And if we're doing an observational science, like a latent space is not a very happy space where to be. So we did this game called hierarchical clustering, where basically we calculate a matrix of correlation factors. This was just Spearman correlation, but we actually tried a few different things. And then you create clusters, right, of features that are very correlated with each other. And then you can actually take, from each one of these clusters, you can extract one, for example, the median. Right? But you still know what features went there. And then you can adjust, clearly you can, cluster more features together or fewer features together. You can adjust it by trying to solve your problems of predicting the properties of galaxies with different amounts of features and figuring out where you stop losing information. Which are the ones that you can put together without losing information. So what did we do? We essentially rediscovered photometry. So these are examples of clusters that we made, are the one in red. And so you can see that the most natural things tend to happen is that you have a lot of neighbor features that are crushed together. But actually, not always. And we found that this was quite successful. We started with examples with 2,000 features. And we could go straight to a space of 100. Without losing any information. We can actually go down to 10 physical-ish features and only sort of lose maybe like 20% in how you can predict parameter. So this was okay. The other thing that we did is to say, okay, what if I add to the brightnesses that we measure some other features that are manually engineered, but in a way that maps what I know about galaxies. And what I know is that information is encoded in gradients at different scales. Right? If I tell you, okay, I want to measure, instantaneous star formation history, you may say H alpha. If I tell you I want to measure age, you can say, 4,000 angstrom break. So we know that these things about the shape, if I just want to know, is this galaxy forming stars, yes or not, you're going to look for a tilt. So the idea of having gradient at different scales was something that seemed to make sense to me. And I actually borrowed from what you do in time series analysis, where if you want to find sort of recurrent or cyclicity of phenomena, you actually have a sliding window where you compute the finite differences of your series with different pace. And so here we did the same, but we actually looked at added finite differences at different scales, like a few angstrom and a few tens and hundreds and thousands, sort of to mimic spectroscopy and narrowband and medium band and broadband photometry. And then we put them all together, and we actually found that it works. It works in reducing the errors that you make in predicting your parameters. Not so much on stellar mass, which at zero order is a linear problem. Like at zero order, like luminosity and mass are proportional to each other, so there's really not much you can improve on the representation you have. But when you try to solve nonlinear problems, such as star formation rates or ages, you actually do better. And so now we have a new set of next steps. And so one idea would be to sort of combine the two. So first you do the super series, and then you do the clustering. And hopefully you end up with a set of features that is more informative, smaller, less correlated. Right? And this is something that then you can use for anything. You can use it for regular acidity fitting. Maybe it works better. Actually, we should try. The other thing is like going back to our distance problem and say, okay, now that I have created a space of features that are efficient and less correlated with each other, am I going to be able to find a better distance metric that is more proportional, like has a nicer or tighter proportionality relation with the errors that I make? And so, the idea would be like to see if I can tighten this relationship. So the final bit that I wanted to talk about in, adventures in studying galaxies with simulations is actually relatively new, which means still a bit rough around the edges. So this is the first time I talk about it. And this is work that we're doing at CUNY with Festa Businka, who's our grad student, who's actually here today, and Ari Mahler. And the idea is, a lot of times we use machine learning to solve problems. And I think this was the hype. But now I think there is a new side of machine learning tools that is emerging, which is, can I use simulations and machine learning to inform physical models? Can I learn some physics that then acts as an inspiration to create, physical scaling relationships? So I'll tell you what we have been playing with. The problem that we were thinking about is, what are the galaxy and halo properties that drive the sizes of galaxies? Right? This is a plot that really, I put it there because sometimes I need to put plots. Unfortunately, I don't work with images, like I have very few chances for like colorful things. But I think here, this is just showing that there is some observed relationship between the sizes of galaxies and their mass. Right? What we're really interested in is, this makes sense. More massive, bigger. There's also a relation between like spin and size. We're really interested in the scatter. And the idea is that we do have theoretical models of what things are important, but these models, still leave this unexplained variance, this unexplained scatter. So we wanted to see, can we actually learn something from the simulations that then, gives us an hypothesis to test on real data. And so we set up to do this in a completely data-driven approach. I'll tell you how this went. And we're also interested in looking at whether, again, from the simulation, or at least in the simulations, we can figure out what are the most important properties that drive the sizes. And finally, perhaps most importantly, can we derive a physical model? When I say a physical model here, I'm just saying a glorified scaling relationship. So we, as a playground, we use the TNG simulations. And this means just that we looked at dark matter-only merger trees, and then we use a semi-analytic model to calculate the sizes. Okay, so this is just a scatter plot again of like the size here versus mass and halo spin that shows some proportionality and a lot of scatter. Right? So here we are saying, okay, can we do better at interpreting both the trend and the scatter? And this is the easiest case, of course, like for a proof of concept, you always want to go with easiest cases, because here there is an analytical recipe that is known. However, I want to say that up to this point, it's not known to me, it's not known to Festa. The only person who knows about this is Ari. So we decided to run this experiment where, I may be telling you complete rubbish, and this is because of Ari, because he didn't tell me that I would. So I don't know, actually. I can show you where we got, but I actually don't know if it's the correct answer or not. So what we use, we started with machine learning models, and we said, okay, we have a lot of input properties that we have. I think we had, actually, I don't know, here it's 31. I think the final set had 33. Like, a whole bunch of the usual suspect of galaxy and halo properties. Then we use some machine learning models, and here we use random forest and support vector machines. This is tabular data, so no matter what anybody tells you, you never need deep learning on tabular data. And then our target is like some half-mass radius of the galaxies. And, you know, we weren't particularly interested in learning this prediction, right? What we use machine learning for, which I think is a little bit different, is to see if the information was there. We know that these models are pretty sophisticated. We know that they can model fairly complex relationships. In practice, they are not really interpretable, so we don't want this to be the end point. But I think it's a good check to say, is this a solvable problem? And then from there, we could say, okay, you know, like if it is, if we know that the information is present, then can we, you know, figure a way of, you know, finding this relationship analytically? So we did this exercise, and actually, you know, I have to say, unlike what I told you, sometimes the answer is yes. In this case, the answer is yes. We found that we could predict galaxy sizes, which are here on the y-axis. Well, the true ones in the simulations are here. There's a factor of 10 to the negative 3 here. We don't just have giant galaxies that are bigger than the halos. So you can see that this is a, you know, fairly tight relationship. It's hard, you know, like the density of points in scatter plots is always elusive. So here we're using as a measure of how well we do this so-called R2 score, which we can discuss, but it's just some measure of correlation, right? And so here, you know, in machine learning, you usually, you know, train on subset of the data, you apply to the other, you know, this is just good practice. So this 0.92 here is something that doesn't have a direct interpretation, but it just says, hey, you know what? This is doing quite well. So we know that, you know, or we had the idea that it was possible. Now we could also use some of these machine learning tools to figure out which features are important. Now here I would like to focus a bit more on the method than the results, just because this really, according to which subset of galaxies you select, these tend to change a little bit. But this is a method that I think is interesting just to consider and was actually inspired by this paper. And the idea is that you can, you know, let's say you have like 30 features, right? You can build 30 one-feature models. You look at the ones that are most predictive. I mean, this doesn't make a lot of sense, but still. You know, you choose the one that gives you the highest correlation between prediction and truth. And then you add, you know, you select the features, and then you add, you know, all of the other 29. And then you choose the two-feature model that is most predictive. This is nice because it's actually agnostic to the algorithm you're using. You can use it with whatever method you have. And in the end, what we consistently found is that, you know, basically only 5 or 6 are important. In general, we could converge to a set of 10 that work in almost all subset of galaxies that we had. And then we said, okay, maybe we can use this to build a physical model. Now, how do we look for this physical model? We have tools nowadays. This is actually, you know, this looks like, you know, there is a fancy video, but actually it's just a screenshot, okay? And this is, and the only relevant thing of this whole slide is this. So PySR is like, it stands for Python Symbolic Regression, and it uses fancy words to search for equations that fit your data. Right? So, you know, we used to do like, you know, curve fitting. This is something that is similar, but a little bit better. For example, it has a built-in mechanism to reward simple models versus complex one, to reward simple relationship compared to more complex one. And it's by Miles Kramer. So let's see. Now, you know, I want to dedicate a moment once again to all the things that we tried and didn't work at all. The first one is like, okay, this is going to be the completely data-driven approach. Now I have the features, you know, like I feed it to PySR, and then I will get like a beautiful relationship that fits everything. And this like fails spectacularly. So if we use all the features, the entire data set didn't work. Then we said, okay, clearly, you know, one of the problems that we have is once again the sort of curse of redundant features. So we have this problem here, right? We start with 30. We know that so many of them are correlated, but we had extracted our smaller set, 6, 7, 8, 10. So can we do this with 10? No, failure, another failure. Then, you know, I guess like, you know, like Ira and I at this point were like, okay, we'll do it by hand. You know, like Festa, don't look. This is not something you should learn. But, you know, we tried. This also failed. You know, we cried a little bit. And in the end, the only conclusions that we can draw from this, again, in the immortal words of my colleague, is that this stuff is hard. And I think, it seems, I don't know, trivial, but actually I think that this is something where I started this project with an idea that maybe you can do this, but also with the healthy dose of skepticism for what we call completely data-driven models. I just, it sounds nice, but I just don't believe that you can learn science without, sort of like closing your eyes and pretending that you don't know about what are causal relationships and, what things are important. And I feel like this was a confirmation of this. I think that, the illusion that I think somehow, this machine learning hype has created is that you can just take a data set and, unleash some powerful tools and you will learn things that make sense. And I feel like this didn't happen for us, and I'm really convinced that this is just not something that happens. And this was the simplest possible case. This was the case in which we know that there is a simple analytic equation that governs a mechanism that we are looking for, right? So it was eye-opening. I don't think it means that we have to be pessimistic, but I think if anything, it has reinforced the skepticism I have for easy solutions with data-driven tools. So we also had, we were able to make some progress. And so the first things that we decided to do, which was a little bit of an unblinding, but I think, not terrible, was to think, okay, you know what? It is fair to admit that perhaps the process of, forming galaxies and hence the sizes that they have is different according to the morphology of galaxies. Perhaps it is fair to say that disk-like galaxies and elliptical galaxies, because their formation process is so different, will not be governed by the same models. And we had hoped, actually, that these, like symbolic regression or other methods like this, could actually find this difference themselves, right? This is also something plausible. But when it didn't happen, instead what we did is that we divided the galaxies in 6 morphology bins. We didn't really have a morphology label, so we use the mass of the bulge divided by the total mass, or equivalent to the mass of the disk divided by the total mass as a tracer of morphology. And then we use PySR to find, this time more efficiently, some functional dependencies. And then still at that point, we look at each of the 6 bins, we recognize that, they were pointing or hinting to a common relationship, and we said, what, I think here morphology or, this tracer should be the additional parameter that we missed. And we actually had to do this almost by hand. Right? So this is how the sausage is made, but I really don't feel like that there is any other way. And we actually found a formula that is quite functional for galaxies that, where the ratio between the mass of the bulge and the total mass is less than 0.4. I'm going to show you these results. I would say here, the color is mostly for prettiness. It is actually, it does trace the morphology class, but we can look at the different bins. So here, what I'm showing on the left is machine learning, right? This is sort of our target, right? This is, we can discuss the model, but this is almost as well as we can expect to do. And so here we start with very disk-like galaxies at, like B over M of like less than 0.1. And here we evolve towards more elliptical ones. And you can see that, I guess, the performance in predicting sizes, so we have like the true here and the predicted here, is quite good, all the way up to here. Like, even for a random forest model, there's still, you can see that this is not a great fit. There is bias, like the tilt is quite not right. And here you also have a problem in tilt and more scatter. However, machine learning actually still does somewhat decently here. This is the physical model. I still haven't told you what it is. I'm kind of a little bit afraid to do so, in fact. But anyway, you can see that again, in the first 4 bins, it actually has a somewhat comparable performance. Here, it breaks down almost completely, which means that, for galaxies where the bulge is more prominent, really you cannot use the same formula. Again, not a surprise, but something that is, nice to see. And yeah, this is the formula that we found. We are working in a space of dimensionless variable. So every size is normalized by halo size. Every mass is normalized by total stellar mass. And this is the relationship that was picked up with the symbolic regression. And then we realized that there was a trend in the coefficients that we can parameterize with this parameter. So again, this is unfinished work. This is where we are. I don't know if it is right, but one thing that I know is that it works reasonably well. And I think this is a useful, at some point, I suppose Ari will tell us. But I think, it's interesting to know for two reasons. One, if it's right, you can rejoice. If it's not, I think this is really an alert of, look, you really have to be careful about relationship that you find, because the fact that something works doesn't mean that something is true. And so as I mentioned here, we're still in a bit like not doing very well with ellipticals. We do have some evidence that maybe here we are limited by the size of the data. There are, of course, many fewer ellipticals in the data that we have. And you can look at this type of trends using this so-called learning curves. It tells you basically how your measure correlation improves with increasing size of the data set. And the fact that here you still see a slope suggests that if you had more data, perhaps you will be more performant. So we're going to use maybe TNG 300, like much bigger simulation box next to see where we are. Have a few minutes where I want to leave you with some thoughts and two announcements. This is, somehow is like, okay, now some advertising. But I hope you'll forgive me for that. So I guess the concluding thoughts are that I think we are finally over the main machine learning hype, and I say so as someone who jumped on the wagon pretty early, but I really feel like, we saw a lot of papers that were just for the sake of using it, and so now we can actually do the good stuff. And in my opinion, learning better representation of the data and exploring simulations to learn physics are, two of the things that I find interesting to do with machine learning tools. Here we just show a few examples from improving on traditional LCD fitting, learning priors and other things that you can do, evaluating models that are trained on simulations, or formulating hypotheses for physical models. My main conclusion is that it's very tricky stuff. I think one of the big problems is that you have a lot of correlated features, and distinguishing correlation and causation with machine learning, actually with anything, is very, very hard. So I've become more skeptical of any automated pipeline, but I also thought that it's a promising tool, it's fun, it's new, it's exciting. Now for the promise advertising. One is that there is this data science school. It's called it's in the Vatican, so it's the Vatican Observatory Summer School that will happen in June of 2023. And I'm co-chairing this school with Zlatko Ivasic. This is a school that is mostly meant for, master's, early PhD students. It's a month long, so it's going to be a lot of project-based learning. The theme of this year is Data Science Tool for Astronomical Service. And I think it's a really nice venue. There will be there are 2 spots for every country. Financial support is available, and applications are open until October 31st. So I just wanted to put it in your radar. And I think, I haven't been. I'm very excited about this, but what I hear of the venue is that, it's really special. The another flag, hopefully not shameless, is that I've been recording in the past year or so this MOOC. It's a massive open online course in machine learning for physics and astronomy. I wrote a textbook on this that finally will be out next year. It's published by Princeton University Press, but this is not, you don't need to buy the book. But this is a free course that I've been organizing with my students, Olga Privman and Jake Posiglione. And so it has videos, it has quizzes, it has Jupyter notebooks, and all is available for free. And actually, let's see, what time is it? I'm going to see if I can show you. This is the platform where it will be. I do a new window before I reveal that I was Googling magnitude just before this. Actually, this doesn't work. I need to change something here. I wasn't. Let's see if this mirror display works. Yeah. So this will be like the course that we offer. And let's see, am I even logged in? I don't know. Yeah. So these are, like all the topics. And I don't know. I don't even know if we have stuff here. But, you have, it's a basic introduction. It's really something that, I've been teaching for years. Anna, unfortunately, has been on the recipient side of this, so she can tell you more about it. But, hopefully something that really, just anybody that has like a little bit of linear algebra is interested can follow along. And we're hoping to have it out in October. So, you can drop me a line if you're interested, or just, like check it out on this like open learning at Flatiron. And I think at this point, that's really it. I'll leave this here, and thank you so much again.
Thank you so much, Viviana. And at this time, I would like to invite questions from everyone in person and also everyone via Zoom who can record their questions in the chat, and we will get to them that way. So any questions from our in-person audience to start?
Yeah, that was great. I was wondering, how do you know whether you missed like a feature or so? Is that like obvious from?
How do I know whether I miss a feature?
Whether you missed completely modeling a feature in?
Okay, only easy questions from now on, okay? I think this is a great question. I think, there are some features where, you can look at the distribution of something, like in simulations and in data, and just a summary statistic will tell you that something is off, right? On the other hand, I feel like there's a lot of room for confounding effects, right? Because if you're just looking, okay, is this the distribution of, in general, what people do is look at things like, okay, are the distribution of colors, for example, that I obtain in this simulated set the same that I observe? Right? And so this is fine, and this is reasonable, but you're never going to look at all the features that you have. So you're always going to have a lot of things that you don't model too well, and you're really only sensitive to, like the big picture stuff, because these are the type of things that we tend to look for. There's another issue that is like even bigger, which is the fact that we normalize everything at redshift 0. We calibrate everything at redshift 0. And so maybe the colors are fine. Maybe you look at this, but I think if you start opening it and looking at how you get there, I'm pretty sure that there are bigger differences. So the answer is that potentially you could look, if you're looking at a certain feature, if you're looking at a certain emission lines, you can actually look at the distribution in some subset of data and simulation. The problem is also how you make your selection is tricky. So it's more complicated than making it sounds, because you never model all the galaxies in the universe. You never observe all the galaxies in the universe. But in practice, you end up with something that's a lot less sophisticated.
I had a related question. When you were saying that the machine learning was working better when you focused on known features, did you also identify features which were not as known before, which were
Not yet, but I think potentially is possible. We didn't focus on this. Well, we didn't spend, I think this is like a very nice thing to do, like a very nice problem, or just, like going back, sort of, opening up which features are important and trying to map this to why. But we didn't spend time on this. It's one of these things where, it's nice to do and then you never get around to it. But I think it is potentially really interesting.
In the beginning of your talk, you showed the function g of x. How do you decide what that function should be? Is it a linear function?
No, this is, like how we model spectra nowadays, right? Which means that, when I have I think the closest thing is think about one of these, flexible stellar population synthesis models, for example. you make some, you say, okay, if the certain stuff, if this is the star formation history, then I'm going to pick like a library of stellar models, and then I'm going to pick a way in which I model radiative transfer from dust, and you make a lot of these assumptions and you build your function. So I think you're right that we do this as in like, you can interpret this as the most advanced way that we have to make that forward model. That, to say, okay, for a galaxy of this stellar mass and metallicity and star formation history, what do I think with the spectrum will look like? But there is a lot of uncertainty in that as well.
First of all, thank you. And
You're
thank
welcome. Always my pleasure.
So do you have any guidance for the people who are considering building new big surveys? Because the surveys are becoming more and more powerful as we evolve from slow now to data. And enormous amounts of data coming in some sense, predicated on the assumption that some new tools like these are going to help. Should we temporize at some point and just say, let's get all this sorted out before we keep going down the road?
I agree with you like 100%. I think there are two aspects, right? One is that I think so far, I don't know. I think for a long time the assumption was that, like deeper data are always better, right? And I think something that ultimately, hopefully, this sort of like data-driven tools will be able to tell is if you want to learn a certain bit of information, where is information missing? And so this may mean that, I don't know, to give you an example, wherever we have the larger systematic effects, whatever the stellar populations that we can model less well and that are affecting our error budget, these are the ones that we should observe, not just, like galaxies at all redshift or like, stars of all types. So I think ultimately, hopefully this is where we will go, not just, mapping surveys on the basis of improving on a certain baseline that we have now, from a point of view of going deeper or wider, but mapping the information content that we have on the basis of some goal in terms of things that we want to learn, and then identifying gaps.
Just following up on the last discussion. But what about the outliers? Because that's where you have the discoveries, and for that we need to open the space.
Oh, absolutely. Yeah. Again, I don't want to suggest that this is the only thing that you should do. But yes, one of the things that I sometimes make the point of what is also a bit nicer in terms of this tool compared to traditional inference is that when you are just, like looking for data and assuming a model, right, all you do is measuring certain parameters. These parameters only make sense within the context of the model that you have built, and if that model breaks down, then, like the conclusions that you draw don't make sense. And so I think it is, like there's also a lot of, this is more the unsupervised learning regime, but I think, there's also a lot of room for, distinguishing things that are different, either different in a specific way or simply unexpected with respect to the models you have. I think we will have plenty of data that go in the survey direction. So I think, hopefully we also have a lot of room to improve in that aspect.
Well, thank you, everyone, so much for your lovely questions. This is a really fruitful topic, so I'm sure that there will be more. And excitingly, we have space and time to have those conversations with Viviana, since she will be here for the rest of today and also into tomorrow. So please, make a meeting, get on her schedule, and feel free to join us tomorrow at the workshop that she'll be leading on finding mentorship and community in astronomy. So thank you so much. Let's thank our speaker again.